Hi, everyone. Good afternoon. Um, I'm here to talk about Hedwig, which is a shared nothing topic-based pub subsystem. So there are a lot of keywords in there, and I explain what those mean during the talk. Uh, this is work done while I was at Yahoo. I'm now working at Twitter. My background is I worked on Pig during its initial stage, and I also worked on Sherpa, which is Yahoo's internal storage platform. And Hedwig was born out of some of the needs that we saw while building Sherpa, so I'll explain some of that also. Um, so I know technical details can be a little sleep-inducing in the middle of the afternoon, so I'll start with something non-technical, which is why the name Hedwig. So we've had a tradition of naming projects after animal names, and like we had Pig, and then we had Zookeeper to tame all the animals. So Hedwig is Harry Potter's owl, and an owl is supposed to carry messages. So, and a pub subsystem carries messages. So that's the reference. So let me start by describing what publish subscribe is. So you have a bunch of entities which are publishers and a bunch of other systems which are subscribers. And the way it works is the subscribers express interest in a particular topic by saying, hey, I want to subscribe to this topic. And then the publishers go and publish certain messages on certain topics. And the job of the publish subscribe system is to make sure that these messages find their way to the subscribers. Um, and furthermore, the type of publish subscribe systems that we are interested in for the purpose of this talk are the ones that guarantee in-order delivery. So the messages should be delivered to the subscribers in the order in which they were published. And we'll see in a second why that's important. And it also should offer guaranteed delivery. So if a publisher received success for a particular publish call, then that message should uh, without any probability of failure, actually reach all the subscribers. So those are the two requirements, and those requirements basically stem from the use cases we have in mind. And the publish subscribe system is a very powerful primitive while building distributed systems because you can use it to decouple two systems that would otherwise have been tightly coupled. So a recurring theme that we see in all of Hadoop, HBase, is that you want a kind of failover. So you have, like, for example, name node or the edge-based master, and you want high availability or automatic failover. So what you could use is a pub subsystem where you are publishing transaction logs into the system, and the secondary name node or the edge-based master is listening to those messages and can use that for recovery. And if you think about that use case, then it's clear why you need in-order and guaranteed delivery. Similarly, you can use a pub subsystem as a database replication log. So the writes happen at the master, and the writes can be pumped into this publish subscribe system, and all the replicas can be subscribers so that they can apply those updates on their local copy of the database. And that's why in order is important, because if there's an insert and a delete in that order, you don't want to listen. You don't want the replicas to listen to it in the opposite order, because then they would reach a different final state than what the master has reached. So for those two use cases, both in order and guaranteed delivery are very important properties. So there are lots of publish subscribe systems around. I mean, there's Tibco, there's Apache MQ. So why do we choose to build one of our own? So if you look at all those existing enterprise publish subscribe systems, they traditionally offer the guaranteed delivery guarantee, but the way they do it is through the use of a shared disk. So for example, the Tibco user manual says that, hey, if you want guaranteed delivery and you want to be fault tolerant to individual node failures, you can put the messages on a shared disk, such as a NetApp filer. While that might work for some use cases, it has certain downsides. For example, you'll need a significant upfront investment to buy an NetApp filer, so not everyone can afford that. And it's also not incrementally scalable. So if you want to have a small application to begin with that doesn't have that much throughput requirements, you don't want to shell out the money to buy a filer. It's also difficult to share because since it's an upfront investment, you would want to share it among different people, but then you start having isolation issues where one misbehaving application can step on the toes of another application. So these are all the downsides of using a shared disk. So we wanted something that's shared nothing in the spirit of all the systems under the Hadoop ecosystem. So that is precisely what Hedwig offers. It's a guaranteed delivery in-order topic-based pub subsystem, and it's extremely high performance, and I'll show some performance results. Uh, and furthermore, it's elastically scalable, so it doesn't need any significant upfront investment in terms of hardware, and you can deploy it over commodity boxes and can incrementally grow it by adding machines as your throughput needs increase. Uh, and one of the things that often comes with these share nothing apps is high maintenance overhead because you have to move shards around or do a lot of manual maintenance work. But that's something that we want to avoid right from the get-go. So we thought about operational complexity as a first-class concern, and so we've built things like automatic failover and automatic load balancing right into the design. Um, and the other important feature of Hedwig is that it has been designed from day one, keeping the multi-data center case in mind. So as I mentioned earlier, this was built for Sherpa, which is Yahoo internal storage platform. And that is a platform that's replicated across different data centers. So the goal is to use Hedwig as the underlying replication bus, and for that, you do need multi-data center support. So that's something that's been built into Hedwig. So let's look at the architecture of Hedwig. So if you look on the left, there are multiple clients, which can be either publishers or subscribers. So these are your basically application logic that's interested in publishing or receiving messages. And the way they do that is by talking to these components called hubs, which is the core component of Hedwig and which is where all the business logic of Hedwig runs. And the hubs then use two other systems. One is Zookeeper, which you all familiar with. It's and Zookeeper is basically used for storage of metadata. And the metadata in this case is things like what are the different subscribers, how much have they consumed. By consume, I mean a subscriber can actually mark a message saying, I don't need this message anymore, so that the messaging system can then purge it. So such information is kept track of in the metadata system, which is Zookeeper. And then the actual messages themselves are stored in a system called Bookkeeper. A Bookkeeper is actually a sub-project of Zookeeper and deserves its own talk. It's a pretty cool system, but I have a couple of slides just describing the core aspects of Bookkeeper that are relevant to Hedwig. So the published message is actually stored in Bookkeeper. And then if you think about this big box at the top, this is deployment of Hedwig in one data center. And then you can think, the same deployment can be replicated in multiple other data centers. And one data center serves as a subscriber to the other data centers and uses the same protocol to talk to other instances that the clients use to talk to the hubs. So the two protocols mentioned are actually the same protocol. So that's the basic architecture. I can dig into now each of the separate pieces. So let me first talk about Bookkeeper. So the Bookkeeper at a high level is like distributed RAID 10. So what it does is it takes your data and it stripes it and replicates it across multiple machines. Now, distributed RAID is a hard problem, and people have been trying to solve it for a long time. So why would we succeed? Well, for the same reason that HDFS succeeded, we're not trying to be a general file system. We're trying to limit the subset of things that we support to a very narrow subset, and that's basically just an append-only workload. What Bookkeeper does is it takes your append-only workload and stripes it and replicates it across multiple servers. And what you can do is configure things like redundancy, how many replicas of each message do you want. You can also configure the striping, so that how many nodes do you want to stripe your data among, And by increasing the striping factor, you can increase write throughput pretty much linearly. Um, and and since we are append only, we are also able to do a lot of cool optimizations, which I'll mention in the next slide. So as you'll see from our performance results later on, that Bookkeeper is actually very high performance. And what's the reason for that? So if you look at the Bookkeeper server, it only supports one call, which is saying add this entry. And the way it's implemented is very similar to how databases implement the transactional workload. So what happens is when an entry is added, it's first written to a log disk, which says that this entry actually happened, and it's f-synced to disk right away. And in parallel, the same message, well, not in parallel, after the f-sync is succeeded, the same message is appended to a file dedicated to that to the messages entry for that topic. But this file is not f-synced. So if you look at the disk workload here, all the f-syncing is happening sequentially on the log disk. And that's why you can have a very high write throughput. And you can get close to actually sequential disk bandwidth by doing group commit, which is a pretty standard trick in databases. The trick is that instead of immediately f-syncing after every message, you wait for a certain amount of time, let's say 5 milliseconds, and wait for enough messages to accumulate. And if you are running at high throughput, you will accumulate a significant number of messages in 5 milliseconds, and then you can just f-sync them in one batch, and that way you can increase your throughput even more. So we can actually get close to sequential disk bandwidth. So coming back to the architecture, we can now talk about, I won't talk about Zookeeper because that's a system that I'm assuming everyone is familiar with. We'll now talk about the hubs. So what do the hubs do? So hubs, as I said earlier, is where most of the Hedwig action happens. So we horizontally partition the topics across different hubs, such that one topic belongs to only one hub. And the reason we have this restriction, you might ask, like, why not, for more scalability, let the publishes happen on any hub wherever the client wants to do them? The reason is that we want the in-order property, and for forcing an order of publishes, you want all the publishes to go through one machine. So that's why one topic can live on only one hub, but of course, a hub can have multiple topics. And the hub also delivers those messages to the subscribers. And a trick that we use here to increase performance is that the usual use case is that most subscribers are caught on, are like near the tail of the message log. So they are consuming messages that have been published very recently. So what we do is we cache the recently published messages in process in the hub, so that the subscribers can directly retrieve it from there, and they don't have to make the trip all the way to Bookkeeper. So in some sense, Bookkeeper is our persistent store, while hub is our cache. And the hub, the other important function that it serves is it subscribes to the hubs in the other data centers. So remember that Hedwig is built for multi-data center. So the subscribers in each data center should get messages published from all other data centers. And that happens because the hub subscribes to all other data centers and gets the messages published there. And all this is done using fully async network I/O. So there are no, I mean, there are some thread pools, but there's no blocking network I/O, due to which we can really have a lot of high throughput. And it's done using Netty, which is also an open source project. One of the cool things about the hubs is the automatic failover, and this we did to reduce the operational complexity. So if a hub fails, you shouldn't have to manually move topics over to another hub. So the way we achieve that is through the following protocol. So suppose the client wants to publish a message to a particular topic T. The way the Hedwig deployment works is you don't connect to a particular hub, but you connect to like a virtual IP address or some kind of DNS round robin, so that you get forwarded to one of the hubs at random. So let's say you get forwarded to hub C. And since you chose the hub C at random, it's quite probable that that hub is not the owner of the topic T that you're interested in. But if it's the owner, if you got lucky, then it'll just handle that request right away. But if it's not the owner, then it'll go to Zookeeper and figure out if there is an owner. And if there is no owner registered for that topic in Zookeeper, then it will choose one owner And while doing so, it'll take care to pick the least loaded owner. And the way it defines least loaded is because all the hubs report their load information into Zookeeper, so that this choice can be made. And once it's picked the least loaded owner, let's say it chose B, it sends back a redirect saying, hey, client, please connect to hub B. So next time, client connects directly to hub B, not going through the DNS round robin layer, and it sets a special flag in the request saying, hey, I've already been redirected, please don't redirect me again. So this time, the hub B handles the request if it's already the owner, but if it's a new topic, it's never been used before, the hub will actually create an ephemeral node in Zookeeper to establish its ownership. And you can see that how we're using Zookeeper here for both metadata storage as well as for automatic recovery, because if at this point hub B were to fail, the ephemeral node would disappear, and by following exactly the same process for the next publish call, a new owner would be chosen. So all this happens automatically and with no operator intervention. Uh, so for a relatively young open source project, Hedwig is pretty well tested. And for the next few slides, I'm going to just talk about some of the testing that we've done. So one caveat is that these results on really old, relatively crappy commodity boxes that we poor research guys could afford at that time. So just take them with a pinch of salt. Like the results on a server class box of today are going to be much better than this. So these boxes had 2 cores, 2.13 gigahertz, 4 gigabytes of RAM only, and they had 2 disks, and which were SATA drives, 7.2K RPM. And most of these results are on a 4-box farm, which is 1 hub and 3 bookies. Bookies are the Bookkeeper servers. And we've run performance tests, failure tests, and stability tests. So I'll talk about the performance tests first. So out of a publish-subscribe system, the most important thing that you want is good latency and throughput. So you want acceptable latency at large throughput, and this is what this graph shows. So on the x-axis is the throughput, which is the number of messages that we try to publish per second, and the y-axis is the latency as seen by the publisher. We are not measuring the latency of the message making it to the subscriber, but that's pretty small as well. That's not as important as the publisher latency, because when we are able to finish the publish, that's when the transaction is supposed to be committed. So that latency is really important. And the messages that we used were 1 kilobyte in size here, and we had, for every topic that we tested with, there was 1 subscriber and 1 publisher. So as you can see, the latency is well under 10 milliseconds, even for a throughput as high as 8,000 messages per second. And even at that throughput, we got CPU bound because we had only 2 cores. If we had, like, a modern box has around 16 cores, so this would do much better. And we would, I'm pretty sure we can, like, saturate the network card. So the next graph is about scalability, like how the system throughput improves as we add more machines. So the first bar is with the 1 hub and 3 bookies, and then the hub is the bottleneck, so we add 1 more hub. So we have 2 hubs and 3 bookies, and the performance improves. And then at this point, the bookies become the bottleneck. So then we add a bookie, and the performance improves again. So this is just kind of a proof of concept saying, as you add more machines, the system is able to scale. And you can reach, as you can see on the y-axis, you can reach throughputs of like 30,000 messages per second. And that's pretty amazing for a system that offers both in-order and guaranteed delivery. Usually, these kinds of throughputs are seen from only in-memory systems that do not offer any guaranteed delivery. So this is nice that we are able to use sequential properties of disk to offer this kind of throughput, even with the added property of guaranteed delivery. We also tested with large message sizes to verify a hypothesis that it's this CPU-bound nature that's hurting us. So as we increase the message size, the amount of system calls that we have to make for every unit of data that we transfer decreases, because like if you have 100 kilobyte messages, then you're doing only 1 system call to transfer that 100 kilobytes. So you're much more efficient. So as you can see, as we increase the message size, the percentage of network bandwidth, which is shown on the y-axis, the percentage of network bandwidth that we can use increases, which means that we can saturate the network card, and that's always a good thing. So, so that shows that that our network I/O is working in the same way. We also did some failure tests, as I mentioned earlier. So we shot down various components of the system. For example, we shot down one Bookkeeper server, and we were able to see that actually operations continue without a single failure because Bookkeeper has been designed that way, that once a node fails, uh, writing continues to another node, and the change is just recorded in Zookeeper. We're also able to shoot down a hub. In that case, the operations going to that hub will fail, but only for transient time, as this whole ephemeral node disappearing act happens. And once that happens, the topic gets taken up automatically by another hub, which is also nice. We also ran stability tests where we were able to run the system stable for days uh, with a workload running against it all the time. Uh, so let me talk a little bit about the community. This is a fairly new project. We just recently spun it off from Zookeeper. So Bookkeeper became a separate sub-project of Zookeeper. And we have 5 committers right now, spanning 3 organizations. So we have Ben and Ivan and Flavio from Yahoo. We have Dhruva from Facebook, who's contributing primarily to Bookkeeper, and myself from Twitter. In the past, we have had other contributors at Yahoo, Yang Zhang and Irvin Tam. So it's a pretty healthy community, growing, and we hope to do really cool things in the future. So let me give you a brief flavor of what we've been working on in case you want to get involved. It's a really fun project. Uh, some of the things that we've been working on are the following, and these are things that have already been completed. So things like scaling with the number of topics. So earlier, we used to have this design where every topic would get its own separate file within Bookkeeper, and that doesn't scale to hundreds of thousands of topics. So now we have multiple topics shared within the same file, and now we can handle up to 20,000 topics within one Bookkeeper server. Uh, Again, a straightforward feature was garbage collection of consumed logs. So when all the subscribers have indicated that they have they have consumed up to a particular message, then the underlying Bookkeeper ledger can be deleted. And this is something that's implemented now. So these are all the features that we are implementing to get Hedwig ready for production use. The other important feature for production use is Bookkeeper recovery. So as I said earlier, Bookkeeper replicates data between multiple machines. But if you were to lose one machine with a permanent failure, such as a hard disk failure, the degree of replication of your data goes down. So suppose you are replicating with a factor of 2 and you lost one disk. Now you're more susceptible because if you lose that other disk, then you have permanent data loss. So what you would want to do is, after one disk has failed, you want to re-replicate the data so that you can come back to your replication factor of 2. So we have a tool that does that now. It does not run automatically right now, and we intend to keep it that way for some time until we have like totally baked this tool, and we don't want to trigger kind of false recoveries because they can be expensive. Uh, we've also been working on several different client libraries. So we have client libraries both for C++ and Java, and it's not a simple kind of client library for a regular thrift service or something like that, because there are certain optimizations that you can do in a publish-subscribe system that don't fit well with the typical request response style of a regular service. So for example, you can have multiple messages outstanding from the publisher to increase throughput. So you don't have to send one message, then wait for success, and then send another message. You can have multiple messages outstanding on the same connection, and that's something that our client libraries implement. So we have one both for C++ and another for Java. We've also been working on operational/monitoring tools so that Hedwig can export stats that then can be monitored to detect problems and so on. There are several exciting problems to solve ahead, and the goal of this slide is to get some of you excited to join us in solving them. So one is security. This is about preventing unauthorized access to various topics from people or applications that are not supposed to access them. JMS is a Java messaging standard that is already in widespread use, so it would be nice if Hedwig just supported that. Um, Operationalization is a recurring theme, so exporting metrics would be nice. Uh, Subscribing to topic expressions, I'll just skip that for lack of time. Message filters, so sometimes you're interested in a particular topic, but not all messages on that topic, so it would be nice if the filtering can happen on the hub rather than getting all the messages on the client and then filtering them out, because that's wasted bandwidth. Uh, we could also, right now, one hub serves both the publishers and the subscribers for a particular topic. I explained the reason for why all publishers need to go to one hub, because you want to guarantee order. But for subscribers, you can actually serve them from multiple hubs. That's something that we would likely be working on. For multi-data center support, right now, when a message is published in one data center, it gets broadcast to other data centers, but that might not be the best network topology. You might want to come up with a spanning tree to actually route those messages. So that's an advanced feature that we might want to build in. Uh, Multi-protocol support is again an extension of the JMS binding, which is basically make the hub logic self-contained, such that you can just plug in different protocols, so that you can support the RabbitMQ protocol by just writing a small piece, a small amount of code and plugging it in, rather than like re-architecting the whole system. Resources, we have the dev and user mailing lists. And we also have the Bookkeeper web page, where you can go for documentation and setup instructions. The planned users, Sherpa, which is the cloud storage platform at Yahoo, is planning to use Hedwig for as its replication bus. Thrift Store is a storage system that's being built at Twitter, which is also planning to use Hedwig. So it's not used in production yet, but we are going to give it a try. Invite you guys to give it a try and help us improve it and iron out the kinks. And I'm happy to take questions at this point.
You explain that when you add a topic to a hub, you choose the least loaded hub. Subsequently, do you ever rebalance topics among hubs based on workload? And as part of that, is it assumed all the topics are roughly the same size?
Yeah. So basically, we do the least sophisticated thing, which is we don't rebalance right now, and we do assume that that topics are equal.
So hi, over here. So I'm not too familiar with Bookkeeper. Thank you for introducing it a little bit. My question is, why didn't you use HBase or some other mechanism to do all the storing of the data? I mean, did you find it to be too slow for some of the operations that you wanted to do?
So at the time we were building this, HDFS append was not quite ready, and even with HDFS append right now, as we understand it, it's not entirely in order guaranteed ordering within the file. And we're not sure if the throughput will actually match Bookkeeper's design.
Okay, thanks.
I have more like a request rather than a question. So HBase has transaction logs, and maybe one idea that comes to my mind is to make HBase transaction logs be shipped to different data centers via Hedwig. What do you think about that?
Yeah, that's a great idea. I would love for the Edge-based project to move in that direction. That's basically the design that Sherpa has followed. I mean, it's not using Hedwig right now. It's using a proprietary system, but the plan has always been to move to Hedwig. So yeah, the idea that you have is exactly right. I mean, that's the exact use case that Hedwig has been built for.
Hi. I'm trying to understand that what happens when at the consuming the message time. So when consumer picks a message, you need to delete the message from the storage.
Yeah, so when a particular client says consume on a particular message, what the hubs do is advance the pointer for that subscriber, saying, okay, the subscriber has consumed until message ID 1001, so that I won't send that client 1001 again. But there are no strict guarantees, so you might get that message again. But what is guaranteed is that if you have not consumed a message, you will always get it.